thanks, Dominic and Philip, for giving a talk.
Okay. Yeah, hi everyone. We are Philip and Dominic. We're both engine programmers from id Software, as you've already heard. We're actually working at our German Frankfurt office, so we didn't have to board a plane to come here, so that was nice. And yeah, as you can already read, today we'd like to talk a little bit about why and how we implemented a new opaque geometry rendering pipeline for Doom the Dark Ages that ended up using a triangle visibility buffer and a move to fully deferred rendering. Okay, so before diving into the main tech course, let's first start with a quick appetizer trailer of sorts to get everyone on board what Doom the Dark Ages is all about. So we released the game in May this year, and this is an excerpt from our launch trailer. I hope it's not too loud now. Let's see. I'd like to have this speaker set up at my home, please. That's awesome. All right, so what you've seen here is all based on our custom engine called idTech. And idTech, as you might know, has been the driving force behind all of id Software's iconic FPS games for the last decades already now. And contrary to some other large engines out there, it's not super generic or anything. It's really always purpose-built for the types of games we make. And we from the engineering team always try to make it in flux and be quite liberal about replacing parts and adding new features as needed. So with that in mind, when we began production for Doom the Dark Ages and idTech 8, the next iteration, the goals we wanted to reach were kind of obvious, really. So coming from idTech 7 and Doom Eternal, we really wanted more of everything, more or less. So higher triangle counts, more complex material layering system that Billy talked about this morning as well. And yeah, larger map sizes, you name it. And we also needed to support new gameplay elements like the dragon or the big Atlan mech. And all of this always needed to run at 60 FPS on all our major target platforms, of course. So now we entered production for Doom the Dark Ages, and now, fast forward a bit until September 2024. This was roughly 8 months before we intended to ship the title, and all of our major content and game design was more or less done at this point. However, we were unfortunately nowhere really near our intended performance target. So the whole engine department entered a broad optimization phase across the board, since all of the engine features we planned to work on were kind of done already. And some of us, we decided to take a closer look into the performance of opaque geometry rendering in particular. Since, as you might be able to tell from this rather small PIX screenshot here, in some very bad views, only the opaque geometry rendering took half of the GPU frame time. So we decided to take a closer look at what was going on there. So when we started this endeavor, we first wanted to try to understand where exactly do we lose performance there. And initially, we made a couple of observations. Firstly, during that time, we were still using our forward plus rendering approach coming from idTech 7, which means we have actually 2 full geometry passes that are needed. We have one full depth prepass and another monolithic texturing and lighting shader that does all the computation, where another full geometry pass is required. And especially this monolithic texturing and lighting shader, it had at the time already grown quite a lot, both in terms of code size, in features. So we added some more complex material blending, we added parallax occlusion mapping, and so on. And at the time, it had a really large code size, high VGPR count, which made it quite difficult for shader compilers to optimize for and actually produce good code for it. And something we've also noticed is that in those views where the opaque geometry rendering had the worst performance, was in those views that featured a very high triangle density. So with that last point, we wanted to understand this a little bit better. So we actually were suffering from a very bad quad utilization efficiency, which we learned from profiling. But what is quad utilization anyway? So let's take a quick look at some random triangle on screen. And when this triangle gets rasterized by the hardware, we have active pixel shader threads that are launched for each visible pixel that actually contribute something to the final image after all. And the hardware doesn't launch these threads in isolation. It always also dispatches pixel shader threads in 2x2 quads. And these additional helper threads still mostly do the same computations as their active counterparts do, but their result is basically not used in the end. And their purpose is to provide correct derivatives over triangle edges, which are then, for example, needed for texture lots and so on. And the term quad utilization is just the ratio of active threads to the number of overall threads. So in this case, 43%. And the additional overhead from helper threads is relatively small for larger triangles, but it gets worse and worse once we shrink the triangle sizes down. For example, if we shrink that triangle from before down to only a third of its size with fixed resolution, of course, we only get a utilization of 25%. So that's much worse. And this is kind of the trap that many of our worst performing views in the game fell into. And we began looking for ways to address this issue. So how can we actually address this? One thing that we can't do is just simply turn off the quad rasterization method. There's no built-in API, there's no shader compiler flag that you can use, it's just built into the hardware at the moment. One thing we could theoretically do is come up with our own software rasterization scheme, at least for cases where the triangles are sufficiently small on screen. However, this was kind of out of scope already, given our team bandwidth and the time on the project. Instead, we chose to try to limit the impact of the helper threads and avoid them where we can with a bit more reasonable effort. We could make the depth prepass the only geometry rendering pass that we have for our opaque geometry. Helper thread overhead will still be present there, but usually the depth shader is quite limited in shader complexity, and the overall performance impact from additional helper thread overhead will be reduced there. And for the more complex texturing and lighting shader, we try to offload that actually to avoid this hardware rasterization in the first place, for example, by moving that to compute fully. However, if you want to move texturing and lighting into compute, there are several things that we need to solve in order to make this work. First up, we will still at some point need to have triangle attributes. We will need UVs, we will need a tangent frame, and so on. And for this, we decided to implement a triangle visibility buffer, which is essentially just a 2D texture mapping each pixel on screen to its triangle, its mesh triangle, and its instance ID. Also, we need at some point a way to have groups of pixels launched with their correct shader and material. And for that, we are going to dive into, in the next slides, into our material compute dispatch pipeline that we implemented. Also, coming from Doom Eternal and idTech 7, we were relying on hardware-based variable rate shading. And once we move to compute, we can't use this anymore as well. And this is where our variable rate compute shaders comes into play that Philip will be talking about in this presentation a little bit. And we have another presentation this afternoon where we have a deeper dive into that as well. And on top of that, while we're at it, we might still also look into this monolithic texturing lighting shader, which had grown to this monster, basically, and try to separate that into a proper deferred rendering setup with deferred texturing and deferred lighting into their separate passes, with the hope that each of these passes could get away with a lower VGPR count, making it easier for shader compilers to optimize for. And in a way, even during the Forward Plus days, we were kind of already outputting a more or less full G-buffer anyway, since a lot of our post-processing effects, our runtime GI system, already needed information like that. So in a way, we were already paying for some of the downsides you get with deferred rendering, with a high texture bandwidth. We were kind of already paying for that, so we might as well go all the way now. Okay. Before diving into any of the details about this, let's first clarify some common idTech terminology. When we will be talking about a surface, what we mean is basically a part of a mesh that is rendered with only one material and one shader. And when we mention material, what we mean is mostly the texture assignments and the parameters only. We will also always be mentioning the shader separately from that. And we were able to build upon various features that we already had available for us in idTech 7. For example, we already had a large GPU buffer that contained all the streamed in vertex attribute data. And we were also had available like a GPU-driven render pipeline that did all the model culling, all the triangle culling. So we were also able to use that. Also, all our material textures were be able to sample bindless with just indices. Okay, with that out of the way, let's take a closer look at how we generate our visibility buffer. So it's generated during the def pass early in the frame, and we output into a new color render target the hardware provided primitive ID. So in a way, the def pass will become the visibility pass now, which is a term we used to call this pass now internally. And the most important data we store in there is the mesh relative triangle index that's been transformed to its index prior to GPU triangle culling, as well as the surface or instance index. So overall, this is kind of the layout we have in there. We store these two indices, as well as two important flags. One is the triangle binding order, as well as one additional flag that tells us if this pixel is coming from a hardware instancing render path or not. Since in idTech we have these like two different render paths. One is which most of the geometry is using, is the global GPU-driven surface list, and the other one is like hardware instancing, which is only used for small grass clutter and things like that. And we just need this additional flag to tell those two different strategies apart to be able to pull the data from the correct places. So with this data stored in the visibility buffer, so we have like 64 bits per pixel, you might notice that we eventually will need more data than that to perform actual texture, sampling, and lighting. For example, we still need a tangent frame, UVs, and derivatives at some point. And we actually tried to output this as well into a larger visibility buffer. And we actually compared these two approaches. So with our slim variant at 64 bits per pixel, only storing these two indices, we actually saw no additional performance impact at all during the def prepass, since the bottleneck was still on vertex processing, and adding more pixel exports in the pixel shader was essentially free, more or less, in most, like on average at least. And however, when using a fat visibility buffer, which on a double size, where we added the additional data, the performance impact became measurable now as the bottleneck moved to pixel export bandwidth. For us, it was very crucial to stay as fast as we can during the depth prepass, since a lot of the following async compute passes depended on that. That's why we chose the slim visibility buffer variant and decided to actually interpolate the attributes manually later on. All right, we have a visibility buffer generated now. What do we need to do next? We still need to derive some draw codes from it. And for this task, there is actually some really, really good reference already around. For example, the great presentation by James McLaren a few years ago, where they talked about how they employed deferred texturing on their dense vegetation for Horizon Forbidden West. And overall, the two, but yeah, also from Epic Games, they also have like a great presentations, and it even dated back to 2017 from IDOS there. And overall, the two most common approaches we've seen mentioned are what we'll call the quad dispatch and the compute dispatch. The quad dispatch, the general idea is to render one screen space bounding quad for each unique material on screen, and basically early out on the pixels that are not matching this material. And the compute dispatch is basically builds explicit lists of pixels for each material and indirectly dispatches compute group waves over them. So we first thought, hey, this quad dispatch looks kind of easy to implement. Let's go for that first, since we were already pressed on time. So the quad dispatch, well, one of the first things we need to answer there is how to do this early out efficiently. So we render like a material like a quad per material, but this quad will naturally, of course, encompass pixels that we are not interested in, that doesn't belong to this material. And so we could just do a discard in the pixel shader, but this would kind of already be too late, since the whole wave has already launched, and its lifetime will be dependent on the longest running pixel shader thread in there. However, one idea that's been passed around a lot is to use a fake depth buffer instead, which is a depth buffer that we built as an additional full screen pass. That doesn't contain any scene data at all, scene depth at all, but only random, normalized triangle IDs. And then in the actual, when we actually render the material quads, we can bind this depth buffer, set the depth test to equal, and repeat the same fake depth computation logic in its vertex shader. And the result should be that we only get pixels packed in a wave that match this material. So we implemented all of that. And kind of this is the result we got when we also enable like a debug drawing that just draws all the quads that we render in random colors. And at this point, when we saw that, we kind of already became a little bit worried, since that looks kind of crazy. So how does it perform, actually? So this wasn't an improvement at all. So yeah, we were kind of sad about that, and but wanted to dig a little bit further into it. Like, why doesn't it work? So let's do some in-depth profiling here and try to understand what's going on here. So we used Nsight for this step, and yeah, we can kind of see here that we are stalled on the front-end stage due to, so new vertex shader waves are being stalled here, can't launch. And going a little bit further into the depth pixel data flow, we saw that we have a lot of input pixels initially. So a lot of more pixels more than we actually have pixels on screen due to the high overlap of these quads. And importantly, hierarchical Z culling, which happens during coarse rasterization on NVIDIA hardware, isn't really doing a very good job of culling a lot of these. So we still have a lot of pixels to process after that. And most of the work is only being done during early Z culling, which already happens during fine rasterization, where individual pixels are looked at. So our kind of interpretation of that is that with our fake depth buffer, that doesn't contain any structured data at all, it just contains random material IDs, hierarchical Z culling isn't really effective at all, and fine rasterization has just too much work to do. So we actually tried a few variants of this approach, such as locking the material quads to a screen space grid, but we weren't really happy with either of these approaches, so we decided to also implement the compute dispatch approach. All right, before taking a closer look at how we implemented that compute dispatch variant, let's first take a step back and think about what makes a forward plus shader actually perform well. So with forward plus rendering, we were kind of in a best case scenario, since since all the material and entity constants just came from the same, were read uniformly across the wave, which also means that all the material textures were sampled uniformly. And importantly, this uniformity was already known at compile time, so the shader compilers were able to use less VGPRs and output more optimal instructions. And whenever we think about like how do we want to design and come up with a compute dispatch wave packing, we need to try to maintain this texture and material uniformity as best as possible. Okay, so with that in mind, let's dive into some details about how our material dispatch works. So our idea loosely follows the ideas already presented in the Horizon presentation a few years ago. The core idea is to process the visibility buffer in tiles. We chose a tile size of 256 by 256 pixels. And in these tiles, several materials and shaders could be present. And the goal is to write all pixel coordinates in a tile that can come from the same material and same shader into continuous ranges within a large pixel commands buffer. And later, we will use these buffer ranges to dispatch indirect compute groups over them. So as I've just noted, it's very important from a performance perspective that we never process more than one material per wave. That's why we actually add additional invalid padding pixels to this pixel command buffer to pad the pixel coordinate ranges up to the current hardware's GPU wave size. And we still need to answer one important question, like how do we come up with actual positions in that pixel commands buffer? Where should we write our data to? And for that, we have another series of compute passes that run before that. And in the initial pass, we just have a large buffer that where we count all the materials per tile, material, and shader pipeline. And internally, we are working with a logical buffer layout there that would support, in theory, that all materials and all shader pipelines could be present in only one tile. And in order to not blow up our memory budget out of the water with this, we actually only consider the visible shader pipelines and materials that actually use deferred texturing in the first place. And we modified our GPU-based gather and culling pipeline that we already had during the idTech 7 days to perform this additional step as well. So we have like an additional registration step there for all the deferred texturing pipelines and shaders that we actually want during this frame. And importantly, whenever we notice that we run out of material ID slots that we support for this deferred texturing approach, we actually gracefully fall back to rendering these materials that don't fit anymore with the traditional forward plus rendering approach. So throughout this entire time, we have always maintained both rendering strategies alive. And we were easily able to toggle the correct rendering approach based on various conditions like these. So with these counts generated, we run a hierarchical prefix sum operation over them. So we get the overall number of pixels for each tile, material, and shader. And then we just use these offsets to come up with the correct positions each tile and each material should get in the pixel commands buffer. And then we do these, the other compute paths that from the previous slide, where we just write out the pixel command buffer coordinates. And from there, that's not in the slide here, from there we just build from the pixel commands buffer and the list of materials, build an indirect argument, build indirect dispatch arguments that we just then launch from the CPU. And this launch on the CPU side is done like this. So we iterate on the CPU side, we iterate all the different deferred texturing shader pipelines, and for each of them, call one multi-indirect dispatch call to launch all threads within a waves for all threads, all waves within a tile for each for all materials that are in this tile. And each single dispatch within the multi-dispatch contains all waves within a single tile. And in each dispatched shader, we'll then need to find out which pixel it is that we are currently processing. And we do this by reading the current dispatch ID, which encodes both the shader pipeline and tile index. And using this information, we can look up into our offset buffers that we computed earlier and retrieve the tile's local pixel coordinate from there. However, one difficulty we faced is that a multi-indirect dispatch call is actually not something that is available in Vulkan. and PS5 for that matter. So it's only available on D3D12, and then also only when we use a custom command signature there. So on all other platforms, we actually needed to emulate that by combining multiple dispatches into the same group dimension in X dimension. And we additionally split this apart into different power of 2 sized buckets of exponentially larger size. And we pick the bucket that kind of just matches the best the indirect argument group count, so the number of pixels. And we count up the individual dispatches in the Y dimension of the indirect argument groups counts, which becomes then our dispatch ID, basically. And with this emulation, we kind of didn't see much performance loss there, only a bit of more memory. OK, so after we had implemented all of that, we still didn't have any shader logic that we could actually execute from it. But we could already come up with some simple debug tools to test and verify the correctness of it all. So what you see here in this video is me iterating a few debug visualizations that we had. The first one just renders all the tiles and prints out the number of pixels per pipeline that are classified there with our compute dispatch logic. And so these are all debug visualizations that are entirely made on our shader side. So we have shader printf support, shader asserts, and even shader primitive drawing. Yeah, and this is a second debug mode that basically already dispatches a real shader program, but that just colors the pixels randomly based on the material ID that is encountered there. And yeah, for us it was, as Billy also mentioned this morning, for us it was really, really valuable to spend time on these debugging tools like shader printfs, shader asserts to be able to iterate quickly. All right, so we can render random colors very, very efficiently now. So next, of course, we have to deal with textures and lighting. And as a reminder, we picked the slim visibility buffer earlier, and so we still need to do vertex attribute interpolation manually at some place. And we decided to do this in a dedicated compute path. We could have also chosen to do this inline in the texturing or lighting shader, but in our experiments, that increased the VGBR count a lot. And also, we would have to do this 2 times since we already also were working on splitting deferred texturing and deferred lighting apart. So we would have had to do this attribute interpolation in 2 places. So we decided to do this on async compute instead, combined together with the compute dispatch logic generation, so building up this pixel command buffer and indirect arguments. And yeah, so this is running, I think, during shadow rendering for us. Yeah. And the actual interpolation math is nothing really new, so it's not really shown here. We basically just picked up some paper from the 90s, and which detailed how software rasterizers worked back then, and figured out the math from there. And what we ended up computing and storing into these buffers are the barycentric coordinates, the barycentric derivatives, with some packed flags. So we stole 1 bit from the float 16s there, and also the well-spaced tangent frame. And using the barycentrics, we could later, in the actual shaders, just use those barycentrics to fetch and interpolate the needed vertex attributes. All right, so with that out of the way, let's actually look at some performance results now. So for this initial evaluation version, we were still using a combined texturing and lighting shader to better compare it with the Forward Plus version, which also did the texturing and lighting combined. And luckily, this performed much better now. So we went from 14.3 milliseconds on Forward Plus to just 10.4, roughly. And one caveat, of course, to note here is that the performance benefit vary a lot with scene complexity. As long as you have a big helper thread overhead, you get pretty good speedups. So it's kind of like a worst-case optimization that we did here. But as soon as you have like large triangles on screen, such as when looking down at the ground and there's like only one screen-filling triangle there, you don't get a lot of benefit out of it. However, importantly, we were also never slower than the forward plus approach. That's why we went ahead and actually implemented the whole deferred texturing approach for all our opaque geometry and not just for individual single types of it. All right. Next, we still have to work on splitting up deferred texturing and deferred lighting into their own separate passes. So first, we run deferred texturing, which is executed by the compute dispatch logic presented earlier. And in our idTech-specific shader language, which you can see up here as a pseudocode, we actually have we added support for an additional stage here, a compute shader stage. And the existing vertex and pixel shader stage was still active, so you have to imagine lots of code here. And these would be picked if this material or entity is rendered doing forward plus, and the compute stage would be picked for deferred texturing. And okay, and the deferred texturing shader shares most of the code with its forward plus pixel shader variant, but it stops until evaluating all the material layer texture blending and doesn't do any decals or lighting. It just outputs the results into a fairly standard G-buffer that we, as I said, already kind of had. All right. When evaluating the deferred texturing performance, one thing we noticed is that while the compute dispatch wave packing already ensures material and texture sampling uniformity, in a wave, we could still run into a situation where multiple pixels that are processed within one wave could be coming from different entities or meshes. So the parameters related to meshes or entities would still be processed in a divergent manner. And when this is the case, we still get a little bit of an VGPR overhead and less efficient code generation. So one thing that we observed is actually that in most cases, we actually do have all pixels only coming from the same mesh or entity. And we can leverage this fact with a super simple trick. Come on. We actually launch each deferred texturing shader not only once, but actually 2 times in 2 different permutations. One permutation supports divergent mesh parameters, and the other one assumes uniform mesh parameters. And we check it in the shader using subgroup ops if the relevant assumption is met. And if not, if that's not the case, we just early out because we know the other permutation will handle this pixel. So this was a notable speed up for us, but in hindsight, it was a bit of a hack maybe that we added very late in the project. And it might be better to just factor that into the pixel command buffer building in the first place, which we might look into next. OK, this concludes my part of the talk, and I'm handing over to Philip now, who's going to talk a bit about deferred rendering.
Thank you, Dominic. The second part of this talk will be about the other rendering, deferred rendering stages in our pipeline, which is, in that case, deferred lighting and our G-buffer update stage. We learn how to optimize those with a thing that we call tile classification and our own take on software variable rate shading. We skip on a lot of passes that might be interesting, like GI, how we render other things, but we have talks from Thiago, for example, where you could look into that. It's a bit more focused on our opaque pipeline. So now we have a G-buffer with all the solid objects in it, so now what? We have to modify the G-buffer with additional effects, such as our geometric decals, projective decals, wetness, rain modifications, triplanar blood blending. We have a lot of things that are not really part of the object or of the material, but comes from dynamically from other systems. And finally, we can compute the lighting, evaluate the shadow maps, etc. And this won't touch the G-buffer anymore and only store out to a single final lighting target. One detail, we experimented with the option to do this either in one pass or in 2 passes. Like in one pass, which is our combined solution, that means we output both the lighting, like the final pixel, and the G-buffer in one single compute dispatch. The advantage here is that we keep everything in registers, right? And we only need to read the gbuffer once and then write it again. However, again, Dominic mentioned it with our forward plus rendering pipeline, the shaders were quite complex, quite cramped. And then we faced the same problem again. Like when we do so much different stuff in the same shader, it makes it very difficult to keep the vector registers low, occupancy high. And also we found that shader compilers start struggling to optimize such complex shaders. So sometimes you make a change and you get like a completely different ISA afterwards. And if the shader is simpler, it's more predictable. So you can really see, okay, the compiler has a hard time to optimize it. The other option that we explored was splitting it into two passes, into two phases. And in our split setup, we have like one additional gbuffer read, but we have less complex shaders. And we have to dispatch the twice the amount of compute waves. But each of the passes is simpler and faster all in all. And interestingly, on most platforms, we've seen a speed up there by just splitting those passes. So as an example, this is like the finally lit scene only based on the gbuffer that contains our opaque geometry coming from deferred lighting. Without further modification, basically. This is the same theme with geometric decals added on top. Nothing really special. We talked about that in the SIGGRAPH 2020 talk, rendering the hellscape of Doom Eternal, if you want to look up that. And we added projective decals. Also nothing super out of the ordinary, just some boxes projecting different materials and blend into the existing gbuffer. Of course, we do this all in the same shader. All of the decals are clustered, so we can look them up in a uniform way and just project them. The third thing is triplanar blood. So our triplanar blood can basically cover the whole world, and all the puddles will blend seamlessly using a tiled material. They will also be going into the cracks and crevices of our height map, which is also already available in the gbuffer, so that's quite easy. And this scene doesn't have rain, so there's no environment wetness going on in this scene, but this would be done in the same pass. Like what you see here is actually done like in a single compute pass. Next, deferred lighting, or the usual way to run those things, like deferred lighting and gbuffer updates, is just to run a full screen dispatch with a single Uber shader. And that's what we did for quite a long time. And modern GPUs are pretty good with branching features away, but their performance is still heavily dependent on wave occupancy and vector register usage. So now we have a big compute shader with all the features that we support in it. And those features include, for example, multiple BRDFs, shadow map evaluations, decal blending, and all those things. And some features actually use long-lived registers that get allocated at the beginning and will be held to the end. And with increased complexity, we'll end up with a lot of VGPRs. And even if no pixel actually hits that branch, that causes the register allocation. And we can clearly do better. So the idea here in this optimization is to run a different tailor-made shader permutation for a specific set of shader features. And our approach is to chop the screen into, again, tiles, 32 by 32 pixel tiles, in order to dispatch different shaders for each of the tile. And note that the tile size actually matches our clustered bin size. So this way, we can easily check if a tile is touched by at least one decal or a shadow casting spotlight or something like that. So this resolves into a simple scalar lookup. Another benefit is that we can completely skip dispatching compute waves for pixels that are not needed. For example, in the sky, we don't need any lighting. We need to run gbuffer updates. The sky will never receive any decals. So what you typically do is like checking in the shader if this is like if the depth value is something like that, or if this is just the sky. But you still need to dispatch this compute thread. And if we don't dispatch it at all, it's just better, since we don't have to run anything. So how does it work? Our tile classification. Each tile stores a 32-bit bit mask with an arbitrary amount of feature bits. And we assign those feature bits to each tile throughout the frame in different passes. So for example, a material shader knows whether it's a skin or cloth material. So it sets that feature in order to use a different BRDF later. So what we then just do is like adding this specific bit to the tile. And a tile sets a feature bit if at least one pixel in that tile has that feature enabled. So we use in this, it's actually, it's a bit pseudocode, but it's actually pretty much what we're doing. So we're using an atomic bitwise OR to set the feature on a tile, and we optimize that by scalarization. So we do it only once per wave, and this works really well since the wave size is usually, or in our case, really always a subset of our tile classification tile size. And after this simple scalarization, the tile classification cost was essentially completely gone from the profiler, even if every pixel on the screen would set at least one feature bit. So once we have a tile feature grid, we can start generating workloads for it. And a predefined set of features translate to a dispatch workload for a specific path. I'm coming back to those terms later. And each of those workloads will be translated to an indirect dispatch call. And each tile that is part of the workload will become an indirect argument, an entry in the indirect argument buffer. Additionally, we have to store the tile count per workload and the tile position per tile encoded as a 1D index. Again, I'll explain a bit why we have to do this. And in this dispatch shader, where we actually dispatch the thing that we actually want to do, like the lighting or the gbuffer update or composite or whatever, we have to reconstruct the original 2D screen position from that 1D index and the dispatch thread ID. So let's do a little example for illustration purposes. Imagine a tile only has one feature, which is opaque, really like our simplest case. We can run a very basic lighting shader, which is in that case the blue workload. The tile additionally has the BRDF cloth feature. That means that at least one pixel in the tile has cloth shading enabled. And this generates the second workload, which translates to a different set of tiles on the screen. And the third one, for illustration again, is a little bit more complex. So it has like skin or decal, so the shader just has more features in it. That translates to the orange workload, which covers different tiles on the screen again. The white workloads are those that don't have any features at all, so they don't get dispatched at all. This is what we want. This is the cheapest case where we don't even have to check anything in the shader. But let's look at some scene in the game. This is from our map, Argent Forest, I think, that section. And the scene has a variety of different geometry types and materials and BRDFs, so that makes it good for this, showing this purpose. So for tile classification, we added the debug view to inspect all the tile features with the mouse. And it might be hard to spot from this direction, actually. But you can see all the classification bits resolved as a list, so we can see what this tile contains. OK, yeah. Zooming in, we can see that this particular tile classified the opaque features, environment, wetness, drops or drips, puddles, and sun caustics, for whatever, like arbitrarily chosen. But let's investigate a real-world example in the game. So that's the workload for the deferred lighting in this split scenario that I was talking about before, without the gbuffer modifications like decals. So it's only the lighting here. And the debug view above tells us that we need 65,200 and 80 thread groups to cover the full screen, theoretically, when dispatching with an 8x4 thread group layout. And in practice, we've seen in the debug view above, we only dispatch 95 of the groups. So 5% in that case are discarded early. Those are the white not workloads, the white discarded tiles. So those tiles are basically entirely covered by Sky. And out of the 95 groups that we dispatched, we have around 38? Yes, 38 default. My notes, my eyes. Yeah, we have around 38 default workloads in red, and those are the most expensive shaders. These are basically the shaders that contain the whole feature set. We also have 25% of green tiles that run the feature subset 0, that we call it, and those shaders use a little cheaper shader, but we can still do better with the blue workload, and we have 31% of the screen are covered by the blue tiles, which are the cheapest, and that means the lighting shader uses the least amount of VGPRs and runs significantly faster. Printed out some VGPR allocations here. I think that was for Xbox, so you see the actual occupancy jumps in it, and this really makes a difference. And again, note, if we would dispatch a single shader, just full screen with all the features branched, we'd always pay the cost for the red workload because that contains all the features. Next are again 3 workloads for the gbuffer update. So the same classification, but evaluated for a different path. So when we look at the VGPRs, we should actually try to shuffle a bit between green and blue because there's no difference in occupancy. At least not for wave 32. But we're still discarding 32% of all the thread groups, simply because those are tiles that don't contain anything that needs update on the gbuffer, so there's no decal, no wetness, and no nothing. And again, we have the color coding of red, green, and blue that translates to 3 different shader permutations of the gbuffer update shader. But we're not only using that for the deferred lighting, we're using it for almost all the full screen compute passes. So yeah, any compute pass is able to use that, which needs like different treatment for different shaders for different parts of the screen. So in that case, we are looking at our deferred screen space subsurface scattering filter. And we are discarding 62% of the groups. So only the groups with red actually need the SSS filtering. The gun and the shield is still classified as that because internal reasons, our dual spec, a dual lobes specular basically uses the same code path. So it's also classified as like this SSS workload and treated later, but it's just a detail. So an interesting anecdote in that case, like even if we only would dispatch a few pixels on the screen that needed SSS without the systems, we still paid the cost of like 200 microseconds just to dispatch the shaders, like all the filter chain, check them for early outs, and actually do nothing, but we always had to pay this cost. 200 microseconds might not be much, but if you're targeting 16 milliseconds as a total budget, like every microsecond count actually. So we can avoid those costs upfront pretty elegantly. So next is a bit more summary and gets a bit philosophical. Since we added all of that really late, and we need to make sure that we do not introduce any subtle visual differences, because the game was done, and the lighting was done, the materials were done, and nothing would be worse if we could go ahead and change things, and artists would be angry at us just because we optimize something and then things look different or some corner is flickering. So for that, we developed a range of different internal debug tools that we actually used daily to verify every shader change or every change that we did. And again, I can't stress enough how important good rendering debug facilities are. I mean, Dominic mentioned already, like we have those shader printfs, putting out arbitrary colors on screen, debug geometry to render the grid that we've seen before. And this is super important because you can just add them in the shader. It's really a programmer tool. And especially they need to be reliable, real-time, and easy to use. And basically you hit a button, you reload the shader, and you have your debug visualization. I think that things like nightly regression tests, visual regression tests, they are great for some purposes, but sometimes they have just like too slow turnarounds. You want to check a feature and you want to see how it's different to what you did before, so you don't want to rerun the game or wait for the next day. So another tool which is basically, composited of what we already had before, is this vertical slider that compares the forward plus and the deferred version. And what we do here is, well, we use our line drawing and our shader printf features to do it. But what we also do is, in that case, just rendering both render pipelines at the same time, or one after each other. So one is the forward plus version, and we check for the mouse position, okay, then only render the left half, and then we run the complete deferred lighting pipeline, and then there we only override the second pass, the second half of the screen. And this is tied to the mouse, so we can just like go back and forth, and we have things like can zoom into pixels, and we can use the same thing to really check into the corners. And hopefully you don't spot any difference here, because there shouldn't be any, hopefully. This is a thing that I will only touch briefly, since we're going in depth later about this. So in our Gen 9 update for Doom Eternal, we benefited a lot from hardware VRS. So when we ported Doom Eternal from Xbox One to the Series S and X. And as Dominic mentioned already, hardware VRS only works for rasterization passes. So our compute passes are not supported in hardware VRS. So we had to do something about it. And this was quite late in the project, so we started interlooking a technique called variable rate compute shaders as an extension to our hardware VRS. And VRS CS is basically a software implementation of VRS for compute shader workloads. And again, some advertisement. Later today, I'm going much more into details together with Martin Fuller. I think it's at 4 on this stage. Still, let's spend just a few minutes to give some context, just explaining the basic idea. The basic idea is still the same as with hardware VRS, roughly. So we compute a shading rate image by finding neighboring pixels that are similar enough so we can discard some of them. And the goal here is to essentially reduce the amount of uniquely calculated pixels. And with compute shaders, we also have to reschedule them into full waves, so we can retire those other waves early. And the diagram shows a basic set of actions. So we start with our scene luminance from the last frame, and we generate 2 shading rate images out of it. And the first one is the traditional one, has a tile size of 8 by 8 pixels on Xbox, and varying tile size on PC GPUs. And this is used for hardware VRS, so it's really just bound to the pipeline using API calls. And the second one has a tile size of 2 by 2, like it's much more fine-grained, but essentially contains the same information, like what's the shading rate of a different part of the screen. And this is used for VRCS, which is, again, implemented entirely in software. And what we do is we apply VRCS for all of our deferred rendered opaque geometry, and therefore it applies to and optimize most of the things that we presented so far, like deferred texturing, lighting, and gbuffer updates. And our old and trusted hardware VRS is still supported, it's still working, and it's also, of course, used for our transparent geometry, for example, that's still forward rendered, and some of the remaining opaque forward plus rendered geometry. So we've seen a solid win in performance at the comparable image quality, and on the good side, we've seen around 10% improvement of the GPU time in average, which basically translates to 1 to 2 milliseconds according to our budget on the console, which was quite good. And this depends heavily, basically on platform resolution, things like that. So yeah, VRS was a great success for us, but it's also not a silver bullet. We have a lot of corner cases, and it also adds to the complexity of the code base and things like that. We'll cover that later. Let's skip over it. Coming to a conclusion, so what did we do? We essentially shipped a hybrid rendering architecture for our opaque rendering in Doom the Dark Ages. And we added a new visibility buffer and compute-based deferred texturing and lighting approach. And all of that supports both hardware and software VRS. We still support Forward Plus, and we still keep that up to date visually. We compare constantly how it performs. And since we still use it as a fallback technique. And with most new systems, we also have to discuss the pros and cons. Need to be a bit faster. So on the good side, it saved us several milliseconds of GPU performance. And not all cases are a substantial win, but as already mentioned, it was also never a loss. And we're also getting diminishing returns with low triangle density, so which is good because our worst case scenario was optimized. On the bad side, we had quite high memory requirements, and it was quite an effort 8 months before ship. So we really didn't underestimate the time to get there, but we didn't underestimate the portion of the time we need to get the visual parity back. So that was actually a risk. And the ugly part is we have much more complex rendering, so we basically ship 2 different versions of the rendering, which works nicely together. But if you need to find a bug, it's really it became more complicated to pinpoint the issue, because it could be bug in the forward rendering, bug in the deferred rendering. Deferred rendering setup is quite more complex than a straightforward forward approach. Straightforward forward approach. So let's look at some numbers really quick. So this effort resulted in quite big savings in GPU performance for our most critical scenes. So we regularly see savings of around 25% of overall GPU frame time. But this is, of course, depending on content. Could be better, could be worse, could be nothing at all. So we benefited mostly for our worst case scenarios. And another interesting part is when we dropped the internal render resolution with our DRS system, the opaque path performance scales better and almost linearly with the number of pixels. This is also a result of the ratio of helper pixels versus actually visible pixels. So the additional memory costs are quite high. So this is really something we need to consider when we have more time to look into it, because compute is getting cheap and memory is getting not cheap, so that's the expensive part. So we really need to optimize for lower VRAM graphics cards. On 4K currently we need an additional 300 megabytes to drive those techniques, which is quite high, but it's also not catastrophic. The good thing is with lower internal resolutions, this scales down quadratically, so it wasn't really a showstopper for us. And one thing we could investigate more is memory aliasing. We don't do this optimally, since we do this manually still. To hurry up a bit, getting a bit what I had in mind, what we didn't realize for various reasons was running deferred texturing on async compute as well. Of course, we tried it because it's easy to do, but we didn't have a workload on the graphics pipe that really matched this. So it was a net loss in the end. So we kept it on the graphics pipe, serialized basically. Another idea was to use the pixel commands that Dominic showed also for the deferred lighting and the gbuffer update. This is super high on the list on things to try. And This way we could also treat like different lighting permutations like materials, and that would be even more optimal than the tile classification. As said, like reducing the memory footprint, all in all would be nice. Running texturing, decals, and lighting in one shader again is actually something how we started, but then we ran into issues again with register allocations and compiler issues. So we splitted that up, but it's definitely something that we need to revisit if we can get down the complexity and do it in one shader again. So we can get rid of a lot of memory reads and writes. And the next one was like, software rasterization for the visibility pass got really popular. It wasn't really an issue, so that pass is really not expensive for us, so it was not exactly a big deal. Let's get a little bit philosophical and about like what we learned during developing this. So a few thoughts about development practices, our team culture, team interaction, and things like that. So in my opinion, like research papers and concepts on the ideation stage, they are great and important, but often they don't really translate well into practice. So often they work in lab conditions. So therefore we think that we need, if you build new tech, you ideally have to ship it with a game, because this way you have to test it, to test everything against reality. And this is really, really important, at least for us. When you implement something new, you'll see tons of practical hurdles, corner cases. So always and regularly profile performance on min-spec hardware and common user devices, actually. So it's something different to implement something on a 5K developer machine and then trying to run it on a handheld PC for $500. So investing in debug features always pays off. Did we mention that already? I don't know. I think adding major changes late can work. It sounds insane to change your opaque rendering half a year before you ship a big game. But if you have a good team and if you're confident about it and run some numbers and have a good idea about what you want to do, you can take the risk, but always have a good fallback solution. In our case, that was Forward Plus. And teamwork is key. I think that's one of the great things I did software, that everyone embraces teamwork, collaboration between the departments, between different developers, and what we've seen is the result is often more than the sum of its parts. So the contribution of a group can be much, much higher than of individual developers. And that's it. We want to thank you first, the organizers, for this great conversation, and we would like to thank the whole team and everyone. Thank you. Please ask some questions.